Hello everybody. This is the last notes for this school year. What we're talking about here is the last big idea for the calculus class. It's called a definite integral. Okay, so I'm going to give you two videos here. This first one is just kind of talking about the concept, like what is this thing doing and what is it telling us. So it's more about just the idea. The second video will be the process, like how do you do this to get your answer. So here's the idea. Okay, all year long we have been talking about a derivative. Okay, the derivative takes us from a distance to the velocity function, meaning the derivative was the idea of a change. So if we change our distance, we're moving. So the derivative of a distance function gives us the velocity function. Now, over the last little bit, we've been talking about the antiderivative. Hopefully you've been doing that. I haven't seen any questions about it, but I don't know if you're doing it or not. So, here's the idea. The antiderivative goes in the opposite direction. We take the antiderivative of a velocity function, and it gives us a distance function. Okay, the way that looks, that antiderivative was this little integrand symbol. But we take the antiderivative of a velocity, and it gives us the distance function. Okay, so that's a big part of it. Antiderivative takes us from a velocity to a distance. So we're going to go one step further now. So what I got here is just a real basic graph. Here is a velocity function in miles an hour. That's just this constant line right here at 3. So basically it's like you're walking 3 miles an hour. On our x-axis, we have the time in hours. Okay, so if I take the antiderivative of this function, 3, with respect to x, which is really with respect to time, that is going to give us a distance. Remember, antiderivative of velocity is equal to distance. So now, here's the idea. Okay, this it's called a definite integral. It's a little bit different than the antiderivative. We're going to do some of the same things, but it's a little bit different. So the idea here is you are walking 3 miles an hour, and you just stay walking for 3 miles an hour, and you're going out for a couple hours because you got time. So the idea is if you're walking 3 miles an hour and you just walk for 1 hour, you went a distance of 3 miles. If you keep on doing that for 2 hours, you're going 3 miles an hour for 2 hours. You went a distance of 6 miles. If you keep on going because you got the whole day, you walk 3 miles an hour for 4 hours. You went 12 miles. Okay? Everybody can agree with this. Now, where are those distances in this graph? Remember, this is a velocity. It's how fast you're moving. And this is just time. So the idea here is basically we're finding an area. If you're going 3 miles an hour for 4 hours, in between the y-axis from a time of 0 and the x-axis up to 4 hours, this shape right here is a rectangle. If you're walking 3 miles an hour for 4 hours, you've gone a distance of 12 miles. So where is that 12 coming from in this picture? And that's the big idea of this definite integral. 3 miles an hour for 4 hours. That's this area of this rectangle right here. Okay? From 0 to 4 is the base of the rectangle. You're going 3 miles an hour. 3 times 4 is 12. This would be the miles. All right. So here's a little bit of a change in notation. We're taking the antiderivative of our velocity function with respect to x, but we're going to go from 0 hours, so we started walking, and we're going to go for 4 hours. So we put these little numbers here. These are called our upper and lower boundaries. When we take the antiderivative of 3, it gets us a distance function. But when we apply that distance function for our time frames, our answer is 12. All right? So the idea of this is really, it's an area. We're going to put these boundaries on our antiderivative, this integrand symbol, and it's going to give us an area function. So we call it area under the curve. Okay, so let's make a little bit of a distinction here. This antiderivative, it was just giving us a different function. This x squared was the derivative. When we do the antiderivative process, add 1 to that exponent, divide by the new exponent, and then we added that c. Okay, the antiderivative is this notation here. It took us from the derivative to the original function. Great. When we do this definite integral, it is not giving us the original function. What it's doing is giving us the area under the curve. It's going to be a number. And so it looks a little different. We got the upper and lower boundaries, but we're still taking the antiderivative, but when we apply these boundaries, we are going to get a number answer. You're going 3 miles an hour. From a time of 0 to a time of 4, you're going to go 12 miles. Okay? That's the big idea of this material.